Then let me go ahead and put number 12 up here while I'm at it. Number 12, we're going to look at an airplane flying in a loop of radius 170 meters. And the pilot's head always points towards the center of the loop. The speed of the airplane is not constant. The airplane goes slowest at the top of the loop and fastest at the bottom. At the top of the loop, the pilot feels weightless. What's the speed of the airplane at this point? Sad plane. Oh. Oh yeah, you're right. Sorry, sad planes. You know, this is when I was little, I could draw a better plane than this. I don't know. I'm out of practice. I'm sorry. And I only draw planes in this one part of the course, so I kind of forget how to draw them. Yeah. Oh, yeah. Ah, whatever. Okay. Anyway. Velocity to the base, velocity at the top. We're also told that the pilot feels weightless at the top, and then at the bottom of the loop, the speed of the airplane. Oh, we're even given the velocity of the speed of the airplane down here. It's 240 kilometers per hour. And the question is, what's the apparent weight of the pilot at this point? And we're also given that his true weight is 720 newtons. All right. Oh man, I should have done number 13. That's more fun. Oh well. We might still have time. All right, so in this situation, it's still, Newton's law is still true, all right? It's still the case that you can say MA is equal to the net force, all right? But there's a little something extra here, all right? If we look at the centripetal part of the force, right? So if you look right here, right? Well, there's a couple different things going on, right? You got the normal force going up. You've got mg going straight down, right? It's a flat track. You've also got the force of friction directed somewhere. But if it's going in a circle, mass times acceleration isn't up for grabs. We've worked out from calculus another day that the acceleration for something going in a circle, the centripetal part of the acceleration is what? mv squared divided by r. So this is just the centripetal part. That's the center-seeking acceleration. So if I was to draw that on here, and keep in mind this is not a force, I'm just illustrating it. This is the mv squared over r. That's the direction in which that vector goes, center-seeking. So then what? Where's that? What's supplying that? Well, that's the force of friction, right? So in other words, the force of friction has to be pointing towards the center of the circle. Otherwise, the car would not stay on that circular path. But the force of friction is also what? So vertical, what do you got? You got 0 is equal to the normal force minus mg. So therefore, the normal force is equal to mg from the vertical. But the force of friction then, of course, is mu n, which in this case is mu mg. And so there's how you solve it. We just have to look at the m's cancel, and we get v squared over r equals to mu g. Isn't that neat? So it doesn't matter how massive the car is or not, because the force of friction is proportional, and because the the mv squared over r is also proportional to m. It's the same for a car that weighs a kilogram or 1,000 kilograms, at least in this naive model of friction. So then what am I looking for? Oh, mu sub s. So if I'm assuming the maximum force of static friction if I just put an s up here, right? You're like, but it's not static, it's moving, right? But that's the thing, is when a car is not slipping, it's actually rolling the wheel flat onto the ground. So it's still in the static case even though it's moving, because if you look at the surface of the wheel as it contacts the ground, it's always laying flat on the ground. It keeps, laying flat on the ground as it moves. That's the trick. And by the way, if your wheel isn't flat on the ground, if it's slipping, right, you see this sometimes, especially if it's wet. If you hit the gas too hard at a stoplight, your wheel will start spinning, right? Then you're out of the static region, and you've entered the kinetic region. And typically, except for maybe exotic surfaces, the coefficient of kinetic friction will be less. But then there's all kinds of complicated stuff that happens with drag racing in terms of why they spin their wheels. I'm not going to get into that. That's another animal. I digress. All right, so there you go. What's mu? V squared divided by Rg, whatever that is. By the way, the coefficient of friction on dry pavement, I think, is something like 0.9. Rubber on road, rubber on asphalt. On wet pavement, it's something like 0.3. Yeah, it's a lot. That's why you can spin off the road way easier when it's wet. Here I am. If this was 1995, I wouldn't have this problem. Let's see here. So my cell phone would be huge. Let's see here. Divided by parentheses. Why did I just square 230? I'm an idiot. 48 squared. What did you get? Wow. Yeah, so that's tough. That's the answer, though. You're right. All right, so for circular problems, here's the new thing. We use mv squared over r to be equal to the centripetal force. All right, so that's it. Same animal here at the top, right? What do I have? I mean, what's the force on the plane? Right, gravity, mg, and again we have mv squared over r is equal to what? Yeah, centripetal forces, right? Well, I'm thinking there's other forces involved. I'm not sure if I can account for them. There's like lift force of the wings and such. Let's see here. Let me try to work this out here. If we have, let me think about the bottom first. If I know that this is 240 kilometers per hour, then what's mv squared over r? If the true weight's 720 newtons, what's that say mass is? Mass is what? You're like 72 kilograms. No, I know. I want it to be that, but 9.8 meters per second squared. Yeah. What'd you get? 73.5 kilograms. All right, so that's his mass. So then what's mv squared over r at the bottom? $73.5 kilograms. Now 240 kilometers per hour is useless. Let's convert that. That's kilometers over hours, right? We got to do unit conversion here. So let's say 1 hour. How many seconds in an hour? 3,600 seconds. Very good. And how many 1,000 meters in 1 kilometer? So multiply by 1 in this way. And what do we get? Convert the 240 kilometers per hour to blah, 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 meters per second. What do you get? Thank you. 66.67 meters per second. Very good. Roughly speaking. And so the centripetal force that must be at work here is 66.67 meters per second quantity squared, and I have to divide by 170 meters. What's the centripetal force I get? Let's say 1,000. I get 1,922, give or take. Okay. So that's the center-seeking force, right? That is keeping this plane going in a circle. So the same force is basically the normal force that is put on the pilot. So what's his apparent weight? I mean, this would be his apparent weight. Oh, I'm sorry. I got it. I'm still missing something here. I think you have to, if you add 720 to that. Well, that's the centripetal force. If you add 720 to this, you get 2,640 newtons. That's his apparent weight. Is that? So you add his true weight to the mv squared over r to get the apparent weight. So at the top it says he feels weightless. What would that mean? I think so, right? And so that would be V is what? RG, square root of RG. So let's see, that would be .82 meters per second, but what units are we asked to give our answer in? Annoyingly, yes, kilometers per hour. So I divide that by 1,000. That gives me 0.0408 kilometers per second, and then I multiply that by 3,600, and I get 146.9 kilometers per hour. So there's the answer to the first part. Can anybody explain why we should add the apparent weight to mv squared over r? Does that make sense to anybody here? Can you explain why part B we should take mv squared over r and then add his true weight? I think it goes to the question of how does he judge his weight, you know? I don't know. I can't think of a convincing reason for you guys right off the top of my head at the moment. But to find the answer here, we do take this and then we add the 720. Or yours will be different, but sorry. Once that fan turns on, my ability to reason is cut by about a half. So, anyway, there are a bunch of questions I have not yet worked. You can ask me about those next class if you want. You can ask me about what's on the test next class if you want. It's all up to you guys.